Welcome to the second R module. In this video, I'll be walking through the solutions to the second R exercise. You'll also be able to find a written version of these solutions on the class website. The first thing I'm going to do is to start deducer. In this exercise, we'll be using the same data set as in the previous exercise. The data set's called mock class data, and it's provided to you in Excel form. We see two familiar windows on the screen. On the left, we have the console window, and on the right, we have the data viewer window. In order to open the class data, I'm going to click on the Open Data icon on the data viewer window. And then I'm going to navigate to where I have the mock class data set saved onto my computer. For me, that's on the desktop. So I'm going to select that and hit Open. Then Deducer prompts me, asking me which worksheet should be loaded. Since our data only has one worksheet, I'm going to just click OK. And then we see that Deducer was able to load all of our data. I'm going to scroll all the way to the right just to make sure everything was loaded, and scroll down. I have 50 rows. Excellent. So now we're ready to start the exercise. The first problem is asking us whether those people who are varsity athletes in high school currently exercise more than those people who are not varsity athletes in high school. And so question 1A is asking us what statistical test we would use to make this comparison and why. And so the thought process is that we are comparing two unrelated groups, varsity athletes and non-varsity athletes, on a continuous measure. So that's the amount of exercise they have. And so these two things taken together lead us to the conclusion that we want to use the two-sample t-test, otherwise known as the independent samples t-test. Again, the reason why we're using this test instead of the paired t-test is that these two groups are not correlated. Then the question asks us to perform the statistical test, report the p-value for that test, and to also plot the relationship between each group. That's 1C. We're just going to do both at the same time here. So the first step is to look at the console window and select Analysis and Two-Sample Test. This brings up the Two Independent Sample Tests menu. The first thing that we're going to do is to split up our cohort into varsity athletes and non-varsity athletes in high school. So we're going to select varsity and drag that over to Factor, and then we're going to click on Split. I'm going to select 0 into group 1 and 1 into group 2. Now, in this situation, it doesn't really matter where the 0 and 1 go. So I could have 0 in group 2 and 1 in group 1, but realize that this is a neat way. Let's say if you had more than 2 levels, this is a neat way of selecting which two comparisons you wanted to make. So I'm going to hit OK. In the outcomes box, I'm going to drag over the exercise variable because that's what we're trying to compare. In the lower left corner of the menu, we see that the t-test is selected by default, so that's good. I'm going to click on the wrench here just because I want to, or the gear here because I want to see what options we have. And it seems like we have the option to run the t-test assuming unequal variances or equal variances. For now, I'm going to leave this as unequal variances and hit OK. Then you also notice that there's a plots button here. So I'm going to click that and click on horizontal so that it generates a plot for us. And I'm going to hit OK and then run. So notice a few things happened. One is that we have a window that shows two box plots, and we'll address that in a moment. But we also see on the left-hand side that there's an output in the console window. So spreading that out, we see a few things. So we see that the mean level of exercise for those people that have a 0 quoted under varsity. So in English, that means the mean hours of exercise for non-varsity athletes was found to be 3.575, so approximately 3.6, and that the mean for varsity athletes, or the mean of level 1 for varsity, was 4.55. And so we see that there's a difference here in the means. There's a difference of about 1 hour of exercise on average. But then we look at the p-value, which is in the row below that, and we notice that that p-value is 0.21. So our conclusion is that there's no statistically significant difference between the means of these two groups. So said another way, our conclusion is that there's no statistically significant difference in the amount of exercise that people who are varsity athletes in high school get right now versus non-varsity athletes. To reinforce that conclusion, what we're going to do is look at our plot here. It's always a good idea to visualize your data just to make sure you understand what's going on. It can sort of act as a very good sanity check. On the x-axis here, we have exercise. And on the y-axis, we have our two groups, varsity and non-varsity athletes. And we can tell that although the averages are different, there's a significant amount of overlap in how the data is distributed. And so it's not surprising that we came to the result that we could not reject the null. Moving on to problem 2, now we're interested in comparing whether students love math more or whether students love writing more. And the way we're going to do that in this data set is to compare the math love variable and the writing love variable. Pretty convenient. And so the first part of this question asks us what statistical test we would use to make this comparison and why. Well, in this case, what we're going to do is we're going to use a paired t-test. And the reason we're using a paired t-test this time is because these two variables actually are correlated. They are related. And they're related because the same student answered both questions. So student A, you can imagine, would fill out writing love and math love. And if student A really liked school, he or she is going to score those two variables very highly. And so they're related. So the second part of this question asks us how the statistical test differs from the test in question 1. So in question 1, we use the independent samples t-test. And in this question, we're using the paired samples t-test. Now, how are these two different? In question 1, if you remember, what we were doing was we were comparing the mean exercise values, or the mean exercise levels, for two separate groups, varsity athletes and non-varsity athletes. So you can imagine what deducer, or what R is doing in the background, is that it's calculating the mean separately for both groups, and it calculates a standard error for that mean, or a standard deviation. And based on that variation, it's able to compare these two means to say whether there's an actual difference. In a paired t-test, because we want to maintain the correlation, we want to maintain the relationship between the two variables, writing love and math love, what our deducer is actually doing is that it's taking the difference between math love and writing love and seeing if the mean of that difference is different than 0. Let me say that a different way. So in the first question, with the two samples, what we're doing is we're comparing the two means between each other. And in this question, we're calculating a difference between the two variables, and then we're comparing that mean difference with 0 to see if it's statistically significant, to see if there's a statistically significant difference between that mean difference and 0. So the third part of question 2 asks us to perform the statistical test, to report the p-value for it, and to state on average how different are these quote-unquote love scores. So let's do that. I'm going to click Analysis and then go to the Paired Test option here. And what I'm going to do is I'm going to select both Math Love and Writing Love and drag those into the boxes labeled first and second. It doesn't matter into which category you drag each variable. Just keep in mind that the mean difference is going to be flipped. The sign of the mean difference is going to be flipped in the output if you flip these two. So Ttest is selected by default, so that's good. And then I'm just going to hit Run. And we have our output in the console window here. We notice that our p-value is 0.098, which means that we cannot reject the null hypothesis based on an alpha level of 0.05. We would need the p-value to be less than 0.05. So our conclusion is that there's no statistically significant difference between how much people in this cohort like writing versus math. Notice that we come to this conclusion even though the mean difference between the two groups is about 7.5 points, which is illustrated a few lines below the p-value output. Question 3 asks us for an assumption of the previous two tests and that we check this condition for the variable writing love visually. And so what the question's implying is that the variables for a t-test need to be normally distributed. That's one of the assumptions of the t-test. It's a parametric test. As a side note, actually, the paired t-test does not assume normality for the variables, but it assumes normality for the difference between the two variables. So just keep that in mind. So we want to check normality for the writing love variable. And to do that, what we're going to do is plot that variable. So I'm going to select Plots, Plot Builder. I'm going to drag down histogram here and select writing love and just visually look at our output. And so we notice that it doesn't look very normally distributed. It actually looks pretty bimodal with a peak centering around 20% writing love and another peak around 70%. So I would say that this doesn't look very normal. Question 4 leads us to then investigate this relationship further by using a nonparametric test. So question 4 asks us to run the nonparametric version of the test in question 1. So what statistical test will we use to make this comparison? Well, the nonparametric version of the independent samples t-test is called the Wilcoxon rank sum test. And then it's asking us to perform this statistical test. So I'm going to hit cancel here. And the way to do this would be to go to analysis and then go back to two sample test. You'll see that our variables are still where we left them. Exercise is under the outcomes box and varsity is in the factor box. What we need to do here is to uncheck Ttest and check Wilcoxon here because we want the Wilcoxon rank sum test. Then I'm going to hit run. You'll notice it generated a plot for me again because I didn't have it unchecked. The plot should look identical to our previous plot. We look at the p-value in the console window under the Wilcoxon rank sum test heading, and we see that the p-value is equal to 0.19. So this does not change our conclusion. If you remember previously, we had a p-value of 0.21. So it lowers it a little bit actually, but it's still greater than 0.05. So we cannot reject the null. Question 5 is asking us what menu option we would select to perform an ANOVA. So it's basically asking us how we would perform an ANOVA in Deducer and R. Well, if you think about it, an ANOVA is kind of like an extension of a t-test over multiple groups. So it makes sense to have it near the t-test option. So if we're hunting for this, I would go under analysis and try to look somewhere near the two sample test. And I noticed that it says the K-sample test. Well, what is that? So K-sample test actually just means multiple independent samples. So K just being a random number. So a random number of samples. And to back this up, we also see in the bottom left-hand corner, the default test here is a one-way ANOVA. So to run an ANOVA in Deducer, even though we won't actually run one now, you would go to Analysis, select K-sample test, and then select your variables in this menu. Moving on to question 6, so we're now interested in seeing whether there's a difference in whether one considers themselves book smart or street smart based upon whether you played a varsity sport in high school. So 6a asks us what statistical test we would use in this situation. What's different about this question is that the variable for book smart or street smart is categorical. Okay, it's not a continuous variable here because there are only two options. A categorical variable could have more than two levels. It just so happens that there are only two levels here. It's yes book smart or no book smart, which means you consider yourself street smart. And so in this situation, we wouldn't want to use a Ttest. We would want to use a Chi-squared test. So let's do that. So I'm going to close the plot here. And in order to run a Chi-squared test, I'm going to go to Analysis and click on Contingency Tables. And again, it doesn't matter which variables I put into the row or column for the Chi-squared test. So I'm going to drag over varsity as a row, and I'm going to drag over is book smart into the column section. And there are a bunch of menus on the right-hand side here. Let's explore these for a second. So cells allows us to ask for certain percentages or certain values related to the chi-squared test that we want. For now, I'm going to leave these unchecked. Under statistics, we can ask for different tests. The chi-squared test is selected by default, but we can also do the likelihood ratio test, Fish's exact test, and even do a Mantel-Hansel test. I'm going to leave all those unselected for now as well. Results lets us save the results. I'm going to also leave that blank. It's good to know what these menus do. I'm going to hit run for now and see what we have here. So you see this 2x2 table. You see that we have a chi-squared statistic and a p-value associated with that. But what should jump out at you is the low number of cells in the first column here. So because these cell numbers are low, and because one of them is less than 5, I suspect that maybe the chi-squared test is not the best test to use here, and that we should instead be using the Fisher's exact test. And I remember seeing that in the menus before, so I'm going to go select that. So I'm going to click on Analysis and then go to Contingency Tables. The variables are still where we left them, but I'm going to click on Statistics and also select Fisher's exact test. Now the criteria for using Fisher's exact test is really a rule of thumb. There's no hard and fast rule or statistical rule, I guess I should say, where you need to use Fisher's exact test. But I guess it's more accurate to say that Fisher's exact test does a better job of calculating the p-value when the expected cell values are less than 5. I'll say that again in a different way. So the chi-squared test does not do a good job of approximating the p-value of the relationship between two variables when the expected cell value in any of the cells of the contingency table is less than 5. To illustrate that point, I'm going to also select the expected cell counts by clicking on cells and checking expected. I'm going to hit run. You'll notice it generates the same table as before, but there's additional output this time because we had Fisher's exact selected. we see that the chi-squared p-value is 3.19, and the Fisher's exact test p-value is 0.367. You'll see that the Fisher's exact test attenuates the relationship a little bit, and that the chi-squared test it does not do as good of a job when the cell counts are low. Let me scroll up a little bit here. There are extra rows for the expected cell counts, and you'll notice that these are definitely less, that 3.67 is definitely less than 5. So it's correct here to use the Fisher's exact test, or I guess I should say it's more accurate to use the Fisher's exact test in this situation. Our conclusion, of course, is that there's no relationship between these two variables, and that, or said another way, that there's no relationship between whether you played a varsity sport in high school and whether you consider yourself book smart based on the data in this data set. The last question asks us to calculate the risk ratio and the odds ratio for this relationship. This is just a bit of a review exercise here. If you remember, the risk ratio is defined as A over A plus B and C over C plus D. Now, the 2 by 2 here is arranged a little bit differently. If we wanted to calculate the risk ratio for the risk of, this is a little funny saying it this way, but it's the risk of considering yourself book smart given that you played a varsity sport in high school, what you would need to do is flip the rows and flip the columns, such that the box in the upper left-hand corner corresponds to yes, book smart, yes, varsity. Okay, so the formula for this is 25 over 29 divided by 15 over 20. And so that gives us a risk ratio of about 1.15. The odds ratio is defined as AD over BC. And in this case, it would be the same if we flip the rows and columns. So we can just do 25 times 5 divided by 15 times 4 to generate a value of 2.08. And as review, we see that the odds ratio, in fact, does inflate the risk ratio. And that's the end of the exercise and the end of this R module video.